Continue from the last video, we talked about our first example about the jury selection. So here, let's review again when we do the assessment. Remember when we say we have model, then we want to create this model according to the assumption. So how to assess our models? So we will simulate the data according to the assumption. Okay, so in our example, our assumption is the jury selection or the jury panel being selected randomly. Then we can compare the prediction. So the prediction in our model actually just the distribution we simulate. So we compare the prediction to the data that we observe. So in our case here is according to the model, we say we have 26% black eligible juror, then with other 74% for other juror. So then we run 10,000 times. So that's our simulation. So then we compare this simulation result with our data we observe, because in the Robert's case it's 8% only. Okay, so that's we draw this picture. So here we compare them. If the data and the model prediction are not consistent, the evidence against the model. Okay, so that's why we can see here in our result. Okay, so then 8% actually is far from our 10,000 simulation. So that's why we can say the model earlier we say is the jury select is random, but they are really not in Robert's case. So according to our simulation, that we call for Robert Swan's case in the county trial, they do have the statistical bias. So not only his case is 8%, he also provide other evidence. So jury panel draw from the jury box since 1953 is only 10 to 15% compared to the 26%. So the only case which percentage is high is only 23%. So we can see here 10 to 15%, we compare to our simulation. 10 to 15% already kind of the percentage is very small. Okay, so if you can see, we can use the histogram when we talk about how to calculate the percentage. You can see this percent is kind of like less than 5%. So the percent of black panelists was always lower than the expected under random sampling. So we do have the bias. So this bias, when errors are systematically in one direction, so in our direction, they are really much less than our random sample. Okay, so that's our first example. The next example will be a little different. We will have a genetic model. So let's see this genetic model. So this model from the Gregor Mendel in 1822, about 1850. So this model actually, he talked about the pea plants. Okay, so the pea plants for a particular kind. So each one has either purple flowers or white flowers. So Mendel's model is each plant is purple flowering with chance 75%. Also, he didn't say in a range, he just said that's 75% for the purple flowers, regardless the color of other plants. Okay, so our question, of course, is this model good or not? Okay, so this model just say the purple flower has a chance for 75%. So we need to choose our statistic. Okay, so this statistic, we will do what? So one thing is our sample will according to the percentage for the purple flowers. If the purple flowers percentage is much larger or much smaller than 75%, that's an evidence against the model. So on the other hand, because his model specific say the purple flower should be 75%, the absolute value for our sample percent of purple flower should be the key we need to evaluate. So that's why in the statistic at the end, we want to looking for is the sample, the percentage of the sample of purple flowers plants minus 75%. Then we take absolute value. If the statistic is large, that means the evidence against the model. So how to do the Mendel's models? The first thing, of course, this one is either purple flower or white flower. So we can have our predicted proportion. Okay, so this proportion is 75%. That's the purple flower. So the white flower is 25%. And also one thing is, Mendel does have the plants he observed. He observed 929 pea plants, and out of that 709 is purple. So we see his percentage. That will be 76%. But this one is the observed value. So that's at the end we will compare from. So in our model, because according to the model definition and assumption, the purple flower is 75%. So that's what we put here. So our predicted proportion is 75 and 25%. So if we're using the sample proportion, we plug in the observed sample number. So that's 929. So according to this proportion array, so that's we got 74.7 and 25. Okay, so the same thing like we say, this one is the sample you just run. So that's why every time we run, the result will be different. Okay, so we want to make sure we have our model simulate multiple times and large number of times. So that's why here the same thing, that's have our function defined. So we define the sample proportion is according to our proportion array. Then every time our sample size is 929. That's only get the purple flowers percentage, so item 0. So we times 100, so that will be the percentage for purple flower from the sample, from the random sample. Okay, so you can just run one time. So then we run one time, that will be 73, almost 74%. Like we say, our simulation, we need to simulate enough large of time. So that's make a purple array. So that's empty array. So we will run 10,000 times. So that's very similar like earlier how we run the for loop. So our new purple will be, we call the purple flower function. Okay, so then we append the new value to our purple array. So after we got that, so that's make a histogram. So in order to make a histogram, we need to have a table create. So that's the percentage of the purple flower when we have the sample size is 929. That's make the histogram. Okay, so the histogram is big, so that's not sure how should we make that a little smaller. Yeah, so you can see here is the distribution. Yeah, they do have most is 75%. Okay, but we do have some of that kind of have distance on that. So like earlier we say we care about the discrepancy from the sample according to the 75%. Okay, so that's why we want to know we want to see the discrepancy for the sample compared to the model prediction 75%. So that's why here let's add one more let's add a column. Very similar to this table, but we make that a discrepancy for the sample size 929. Then using the purple's array, we minus each one is 75%. So again, we still do the histogram. Okay, so in this histogram, you can see, right, so we think I think to 0 to 0.5% difference is about 58%. So then we have some, correction, this one is not 58% because we need to times the distance. So maybe here is 0.6. So that's about 60% times 6. Here is 24%. Okay, so make sure here the percentage, we all need to use the height times the width. Yeah, so that's the distribution compared to the 75%. So if we just only use the observed result, okay, so then you can see here is the Mendel's, his observation plans. So we just using that to minus 75%. So that's our two example. We have our model and alternative. In the jury selection model, we have the model is we want to have the people on the jury panels were selected at random from the eligible population, eligible juror. But from our simulation and the result, so we can see our distribution about our simulation, the 8% actually is far from our simulation. So we have alternative viewpoint is, no, this model actually is not being fit well. They were biased against black men. Okay, so that's according to the model, that's we have, right? So that's here is, even the court response say, 8% is one of the percent. That's one of the chance, but actually this not really can fit the model we want. We select the jury panel is at the random selection. So in the second case, the genetics. So the genetics model from the Mendel's model, he say each plant have 75% having the purple flower. Okay, so just according to the observed data. Okay, so they are not exact 75%. So our alternative viewpoint is no, it's not. So that's the model we try to create. Then we want to see, do they their prediction meet our real world or not? If not, so then this model is really cannot use for that case. Or we need to have our the assumption for the model may need to be correct or update. So a model is built by the assumption. So we need to assess the model to see that's a good explanation or fit the real world situation we are looking for. So how to assessing a model? Here's the step. The first one, we choose a statistic to measure discrepancy between the model and the data. Then we simulate the statistic under the model assumption. For example, our model assumption for the jury selection, they will have random select. All the eligible juror is random select in the panel. Okay, so that we use that for our simulation. Okay, our simulation should be random. So the assumption we need to make sure we all match and include it in our simulation. So once we have the simulation done, you simulate that statistic. So we will compare the data, the observed data to the model's prediction. So then usually we can draw a histogram of the simulated value of the statistic. We compute the observed statistic from the real sample. If the observed statistic is far from the histogram, that's an evidence against the model. So usually we say they have a bias, then we need to reject the model. Or we need to looking for the new one, or we need to modify the model to better describe and better fit the real world situation. So that's our lecture 16.